So I'm from Germany. I'm 27 years old, and I studied physics bachelor in Heidelberg from 2011 to 2015, and then I studied. I did the fusion EP because I was always. I mean, for me, having this goal of fusion in mind, combined with the experience of studying abroad, was just incredibly attractive for me. And so I studied, as all of you, the fusion EP in Madrid first, the first year, and then the second year in Nancy. And I did not really knew exactly in what field of fusion I want to specify in by then. But as you know, in Nancy, there were like 5 different master topics, and then I took one of them, which was about the numerical investigation of turbulence in a plasma. So actually my master topic was completely different compared to my doctor PhD topic. But actually, so I found my master topic very interesting. It was about trapped particle modes and their interaction between different modes, and how the energy can be transferred from low frequencies to higher frequencies, and also from high frequency to lower frequencies. So, but I kind of wanted to orientate myself rather into a more engineering direction, although you're going to see that my topic is still quite rather physics. But still, this enabled me to take a PhD in Madrid, which is called Material Science and Engineering, and the engineering part of it is that that it's connected to the Eurofusion project in IFMIF. IFMIF, I'm going to tell you about that more, is a device for fusion research as ITER as well, which is still IFMIF donors. It's 2 devices. Donors is kind of an early IFMIF, and it is one step towards towards fusion. Since ITER is rather focusing on studying and proving the physics, the plasma physics, IFMIF is gonna focus and investigate rather the materials which are gonna be used in fusion reactors. And why this is necessary, I'm gonna tell you now. So I'm Sebastian Hendricks, and I'm behind the tritium modeling group of the CIEMAT, the National Fusion Laboratory of Spain. And I'm going to talk with you about the numerical and experimental investigation of yttrium metal as a getter material for the hydrogen hot trap of IFMIF donors. So you're going to see that yttrium is going to be used as a getter material. So a getter material is a material which can absorb another material due to its high solubility of that material. In this case, it's hydrogen or tritium, but it's hydrogen isotopes, you can say. And this is required in the fusion research facility IFMIF donors, but we're going to start from the beginning. So IFMIF means International Fusion Materials Irradiation Facility. And its objective is the irradiation of structural material candidates for DEMO. DEMO is the next fusion research reactor after ITER, which is besides just having high tritium deuterium fusion plasma. Also, it's going to have a breeding blanket system where the tritium, where the tritium is bred where the tritium is bred for the fusion reactor, and at the same time where also the energy of the neutrons is going to be turned into heat. So in this demo, structural material is going to be used. Yes, and the problem is that compared to ITER, where you only have more or less one displacement per atom in the structural materials of ITER due to its rather low neutronic load on the first wall. You can see it here, it's more or less 0.07 megawatts years per square meter. In a real reactor, and almost also the same applies to DEMO, maybe a little bit less. You have 10 to 15 megawatts per year per square meter, and you have displacements per atom of 100 to 150 per year. This means that you have, so you see that in a real reactor compared to ITER, for the materials, there are way different requirements, and to study which, because of the high neutron flux and radiation, and to study these materials, until now you don't now have any device. You don't have any device which can produce a neutron ray, which is comparable to the neutron radiation in a real fusion reactor. So to test materials which are exposed to such a neutron radiation, now this International Fusion Materials Irradiation Facility is going to be built and still under design, and is going to be probably constructed in the next 10 years. However, before IFMIF, an early IFMIF is going to be constructed, which is called DONUS. However, IFMIF, the setup of IFMIF looks like this. We have two accelerators which accelerate deuterium ions onto a lithium target. The lithium target is liquid lithium, and the liquid lithium is flowing in a liquid lithium loop with a quite high velocity. The energy of the deuterium is more or less 40 mega electron volts, and due to nuclear reactions between the deuterium ions and the liquid lithium, that we have a neutron ray produced, which is produced behind the lithium target, which is comparable of its energy with the neutrons in a fusion reactor. And this neutron ray can then be directed on material samples. Whereas DONUS, the early IFMIF, will look principally the same, except that we only have one accelerator and therefore also just 20 mega electron volts. However, to expand it to IFMIF, you just need to add another accelerator. And DONUS means Demo-oriented neutron source. So the reactions between the deuterium and the lithium you are seeing here. You have lithium 6 and lithium 7 again, and you see that on the one hand you have just the reaction deuterium with lithium 7, which produce neutrons, protons, so proteo, which will lead to just normal hydrogen isotope in the liquid, and you have to take into account that beside the neutron, the proton is going to be absorbed by the lithium. So the proton is inside of the lithium after the reaction. The second reaction, you have neutron produced, protium produced, tritium produced, and helium-4 produced. So the tritium and the protium and the helium is going to enter into the liquid lithium loop. Then the neutrons which are created can react with lithium-6, which is also going to produce tritium and helium-4. And you have also more reactions which are going to produce beryllium. The liquid lithium loop, you see it on the left side. As I said, due to the nuclear reaction, you have several other isotopes produced with a certain rate, and this presentation is going to focus on the production of the hydrogen isotopes protium, deuterium, and tritium. And you see here the rates which they are produced, which would mean that 93.4 grams of hydrogen, of total hydrogen isotopes, are produced per year, which is too high. This also means that 3.9 grams of tritium is going to be produced in the liquid lithium loop per year, which needs to be controlled, and it's too high since the tritium can permeate through the walls of the liquid lithium loop and enter into the outer environment. furthermore, also this causes an increase of corrosion. So the requirements for donors they are set by the diffusion community, that the concentration of tritium in the lithium needs to be less than 1 weight parts per million. And therefore, since way more tritium would be produced, we need to add a purification loop to the liquid lithium loop. And hot trapping or gathering is seen to be a useful method to absorb the hydrogen isotopes from the liquid lithium. And since yttrium metal, since yttrium metal has the highest solubility of hydrogen isotopes of the metals that are known, it is since it is chemically works fine with liquid lithium, it is considered as the best getter material. However, it needs to be pretreated with fluorhydride to always keep away a very probable oxide layer on the yttrium metal. A hydrogen tape made of an yttrium pebble bed is capable of fulfilling the mentioned requirements that has been shown in a lot of papers. So you can see here the liquid lithium loop, which is connected in parallel to the normal liquid lithium loop. And you have a cold trap, which removes other impurities, connected in a row with the yttrium hot trap. And the yttrium hot trap, you can imagine, looks like a cylinder, which is filled with a pebble bed. And the pebble beds are simply small balls of more or less 1 millimeter, but let's say in this order of magnitude can also be 1 centimeter. And the temperature of the liquid lithium will be between, let's say, 280 and 350 degrees Celsius. However, it's not now possible to simply choose a random size of yttrium container, fill it with yttrium pebbles, and connect it to the liquid lithium loop. It needs to be exactly studied how the tritium inventory in the liquid lithium evolves with time if we have a certain amount of yttrium connected in a purification loop. And the question is, how much yttrium pebbles are needed to fulfill the requirements for donors, and how big must be the diameter of the pebbles, and so on, and what is the best temperature for the use of this trap. The requirements for donors are transferred to mass, expressed as that the mass of tritium in the trap. This is another requirement. So whereas we have the requirement that the concentration in the liquid lithium loop shall be less than 1 weight per million, we also want now that the mass of the tritium trapped in the tritium trap in the yttrium shall be also less than 0.3 grams. Since in a case of an accident, if all the pebbles fly around the room, of course it might be that the tritium is going out to outgas and completely contaminate the room and the environment. So this is another requirement for donors. So in order to know how much yttrium is needed to fulfill the requirements for donors and how the tritium inventory and the lithium evolves with time, we are going to look on a theory of tritium transport in a metal, let's say. In this case, of tritium transport in liquid lithium and in yttrium. In general, the tritium transport, or the hydrogen transport, is determined by the diffusion of tritium and in liquid lithium and in yttrium. And diffusion is expressed by the diffusion equation, and is described by the fusion equation, which is also the Fick's second law, and is a coupled differential equation, which can you see in the upper right corner. This diffusion equation is simply one equation which you have, but which alone does still not allow you to calculate the whole system. what we want to know is the evolution of the concentration of tritium in the different media, and in the same time also we want to know the flux, or the flux of the tritium through the different media. And therefore we need to understand certain coefficients and certain parameters of the material. For example, we know that the tritium is flowing in the liquid lithium, which is one condition which we have to take into account later. We know also that the flux of tritium is described by the Fick's first law, which you see in the lower part in the yttrium bulk on the bottom, which says that the flux of tritium is proportional to the gradient of the concentration of tritium in the yttrium. In the liquid lithium, you have the same situation, simply that due to the fact that the lithium is moving, this first Fick's law reduces to, due to the fact that the liquid lithium is moving, this leads to the fact that far away from the yttrium bulk, the concentration in the liquid lithium is even, and close to the yttrium bulk, since the hydrogen moves from the liquid lithium into the yttrium, the concentration in the liquid lithium lowers down. So, and we can say that we can now estimate the flux between the liquid lithium and the yttrium, or from the liquid lithium into the yttrium bulk, by simply calculating the gradient as the difference between the concentration far away from the liquid lithium and the concentration at the yttrium interface, and the proportionality factor is included into the constant, which you see in the equation on the lower left part of the display, is AF, which is the mass transfer coefficient. So this is just some equations that you see here. So what you need to calculate the whole system of equations is a certain amount of equations, which is the diffusion equation on the upper right part, the first fixed laws, which you see in the lower left part, and the boundary condition at the interfaces, which is the equilibrium of particle fluxes. So, for example, the flux of particles in the liquid lithium into the yttrium bulk needs to, the JMT needs to be equal to the fluxes of particles in the yttrium bulk at the interface. And moreover, we have the equilibrium of the chemical potential, which says that which can be expressed by this equation, that the concentration in the yttrium at the interface is a certain amount higher than the concentration in the liquid lithium at the interface. And how much it is higher, this factor, how much it is higher, is simply the ratio of the solubilities of tritium in the yttrium compared to the solubility of tritium in the lithium. And the solubility can be quantified by the so-called Sievert's constant. I won't go here more into depth because you will see the expression for the Sievert constant. In case of a pebble, we have a spherical symmetry. And this spherical symmetry is taken into account in the spherical expression of the diffusion equation. So taking the equations on the right, we can now collect the equations which are needed to be calculated in order to be able to get the time evolution of the concentration and the fluxes of tritium in the liquid lithium and in the yttrium bulk. So using these equations, using the boundary condition at the interface and the first Fick's law, we find two equations, which you can see on the left upper part. And these are two equations, but in the two equations, we have four unknown. We have the unknown of the concentration in the lithium with time. We have the unknown of the concentration in the of the tritium in the yttrium at the interface with time. We have the flux inside. We have the unknown of the flux inside of the with the evolution of the flux inside of the pebble at different radius with time, and we have the unknown of the concentration in the yttrium pebble at the different radius with time. But here we only have two equations, so we need two more equations to solve this system of coupled system of equations. Here you can also see that here I put a diagram which shows the CIEMAT constants or the solubility of tritium and yttrium and in lithiums. And you see that in yttrium, the solubility is several orders of magnitude higher than in the lithium. The CIEMAT constant is following an Arrhenius type of equation as in exponentially, as you can see here. And you can see also that with a higher temperature, the solubility is lower than with a lower temperature. So with a low temperature, the solubility increases. Now we define the so-called partitioning coefficient, which is simply the ratio between the solubility in yttrium and in lithium. So in case of, let's say, 350 degrees, it's 3,450. So the solubility would be 3,450 times higher at 350 degrees. And you know that, yes. So the mass transfer coefficient, which I was telling you before, in a pebble bed can be expressed by these equations. And if you plot them with different temperatures, you see that for higher temperature, the mass transfer coefficient is higher, meaning that the flux in the lithium is higher for higher temperatures. What you can see here on the left is, and what you actually need in the end, what you want to know is also the flux of tritium from the lithium into the yttrium. And this is nothing but the flux which is shown on the upper left part. So you can say that you can already estimate the flux is higher with a higher mass transfer coefficient, since it's proportional to the mass transfer coefficient. Also, the flux is higher with higher diffusivity, which you can see on the left. You can see that the diffusivity in the yttrium is in the lithium is higher, is several orders of magnitude, 2 orders of magnitude more or less higher than in the yttrium. And it is also following an Arrhenius type of equation. And in this case, for higher temperature, also the diffusivity is higher. So now we have already seen the first two equations, and now we need a third equation. The third equation is simply the Fick's second law, which describes the concentration profile in an yttrium pebble. And you can see it here. However, it needs to be calculated numerically. And therefore we use simply a finite difference method, as you can see here. I will give you the presentation later, so you can look on it a bit more. And you need the initial condition of the concentration inside of the pebble at time equals 0, and the concentration at time equals 0 in the lithium as well, in order to be able to calculate the whole set, numerically calculate this set of finite difference equation. The fourth equation is simply the total time derivative of the concentration in the liquid lithium, which you can see here. In 1D, for example, it would be that the change of the concentration at with time, with the total time, so the total time derivative includes the time, the change of the concentration at a fixed point with time, and also the change of the concentration at a fixed time with changing location. So, and transferred to, and you can change this equation, so you get you can express this equation, the first equation, also with the variables that I have used before. So you get this equation, which forms the fourth of our equations. Moreover, you can you can express the trap efficiency, which is simply the concentration in the inlet minus the concentration at the outlet divided by the concentration in the inlet. And the retention rate, which is in the end what you want to know. In the end, what you want to know how much tritium is absorbed per time, is then the surface of all the yttrium pebbles multiplied by the average average flux into the yttrium pebbles at the interface. And now we can already say, due to this set of equations, that when the temperature increases, the mass transfer coefficient increases. This means that the diffusivity increases, and the diffusivity in lithium increases, the diffusivity in yttrium increases, and the partitioning coefficient goes down. However, the fact that the partitioning coefficient, which is the ratio of the solubility between yttrium and lithium, goes down, is stronger than the fact that the other variables goes up. So the overall flux into the yttrium goes down, meaning that the retention rate goes down and the efficiency of the trap goes down. If we increase the mass of yttrium and leave the diameter of the pebbles constant, meaning that this means that the number of pebbles goes up, the surface goes up, the retention rate goes up, and the efficiency goes also up. If we increase the diameter of the pebbles and leave the mass of all the yttrium pebbles constant, this means that the surface goes down, the retention rate goes down, and therefore also the trap efficiency goes down. If we increase the mass flow rate of the lithium, this means that the mass transfer coefficient goes up, which then leads to the fact that the flux into the yttrium pebbles goes up, and the retention rate goes up, and then the efficiency of the trap goes also up. So now we have that system of equations, and we can see it as a very big system of coupled differential and algebraic equations, which can only be solved by a solver where you can, let's say, list all the equations that you have, and this program orders all of these equations in the most appropriate way, and then calculates and then solves the system of equations. And we have chosen to use the differential equation solver by EcosimPro that does exactly that. And there you can write different components. So it's a component-oriented language, and you can connect them, and it's simply actually connecting packages of equations together, which is then considered as the system of equations which needs to be solved. So I have written from scratch a numerical model with these equations of the trap, and you can and I just connected it with, let's say, an yttrium tube and a liquid lithium tube, and added the fact that the lithium is moving. And for example, if when I produced the system of a temperature of 300 degrees, a mass of yttrium of 1 kilo, a volume of lithium of 100 liters, and a mass flow rate of 1 liter per second, and a 1 millimeter pebble diameter. And if I chose an initial concentration of tritium in the lithium of 10 Y-ppm, I got that the yttrium pebbles are absorbing the tritium very quickly. You can see here, after 5 hours, we already reached an equilibrium between the tritium in the yttrium and in the liquid lithium. When the chemical equilibrium between the lithium and the yttrium is reached, there's you don't have any further flux into the yttrium pebbles. You can see here the model of the trap, because you can connect different components in the EcosimPro, and then you can assign it to a bigger component, as you can see here. This simulation would mean, as you can see in the lower right diagram, you can see how the mass of the tritium in the yttrium pebbles goes up with time, and the mass of the tritium in the liquid lithium goes down. Here I simulated for you the tritium concentration profile in in one pebble, if let's say a 1 millimeter pebble, with time. So for example, after 1 minute, after 2 minutes, and on the right you see the radius. So on the right part you have the interface between the yttrium and the lithium. So when you see how the tritium concentration goes up after 15 minutes, and due to the diffusion, the tritium moves towards the center. And you see how the tritium inventory in the liquid lithium goes down. But you also see that the gradient of tritium concentration at the interface goes down, meaning that the flux goes down, and this is why the flux stops at some point, because the concentration gradient is almost zero after 5 hours. Here we see the trap efficiency, which is like, it falls down from say 23% to almost, let's say, between 0 and 1% very quickly. And then to study, or to let's say contribute to the design of the trap for IFMIF, I, with EcosimPro, created a liquid lithium loop similar to IFMIF, which simply consists of a hydrogen source. So the source where the concentration of hydrogen, tritium, and deuterium linearly increases. You have here the different parallelly connected loop systems, and on the right you find the Yttrium-trap. And if we run this simulation, we see how the concentration in the yttrium pebble increases with time. So, for example, we have here a liquid lithium volume of 10 square meters, so cubic meters, and we see now that with time the concentration, in general, without any trap, we would have the situation that the concentration of tritium and hydrogen in the lithium would linearly increase. Now with an yttrium trap, we have the situation that still the concentration in the liquid lithium linearly increases, and since the concentration in the liquid lithium increases, we continuously we always find a concentration gradient at the interface, and we see that the profile does not change really its shape. It simply increases the concentration, but the concentration gradients at the different positions at the different radial distances stay more or less the same. So this means that we have more or less a constant flux into the yttrium pebbles, and this means, however, that we will never reach the situation in which the concentration, in which the flux into the yttrium pebbles is as big as the let's say as the production rate of tritium in the liquid lithium, because if that would be the case, the concentration in the liquid lithium would stagnate. This means that very quickly we got a chemical equilibrium between the concentration in the yttrium and the lithium, and the concentration gradient in the yttrium would disappear, meaning that we would not have any more flux into the yttrium pebbles, and this would then again mean that the concentration of tritium and lithium would increase more. So we will always have a concentration increase in the lithium and the concentration increase in the yttrium. Here we see the concentration of tritium increasing with time in the liquid lithium loop in 1 year. And we see, for example, that the concentration of tritium would anyway stay below 1 Y-ppm, even without a trap, because the highest profile is the case without a trap. And for example, with 40 kilograms of yttrium, we would always stay below, let's say, 0.05 Y-ppm. And so the higher mass of the pebble bed leads to a less steep linear ascent of the concentration. For example, but now we wanted also that the mass of tritium in the trap does not goes above 0.3 grams. So we see it here in the line. So for example, if we took a 1 kilogram trap, this would mean more or less that after 150 days, the trap would contain 0.3 grams of tritium. Or if we take, for example, 40 kilograms trap, this would mean that already after like 25 days, the trap would reach 0.3 grams. So the maximum allowed tritium inventory in the trap is reached within a couple of months already. And the only way of, and how to let's say fulfill this requirement and also fulfill the requirement of the concentration is to change the trap always when 0.3 grams are reached in the trap. Also here we see the trap efficiency for different masses of yttrium in the trap. For example, only for 40 kilograms, we would always stay above 1% during the whole year, since the tritium concentration in the lithium rises. So, and the trap efficiency decreases rapidly, which directly follows from the equation. Here you see then how, due to the change of the tritium solubility, a higher temperature leads to a less efficient trap. So you see here for the same amount of yttrium, how the concentration increases, let's say, less fast for lower temperature and increases faster for higher temperature. Here you see how the concentration in the lithium increases for different pebble diameters, and we see that, for example, for between 1 and 5 millimeter pebbles, we almost don't have any difference of the tritium efficiency. But at, let's say, 20 millimeter pebbles, we would already see a difference. So as I said, I propose now the requirements for donors that the mass of tritium in the yttrium pebbles shall be below 0.3 grams. And we can also say, for example, that we want the mass of tritium in the liquid lithium to be always below 0.3 grams, which, for example, means in the case of an accident, and if all the tritium would be released from the yttrium and from the lithium, we would only have 0.6 grams of tritium coming out gas into the environment. For example, if we now change the trap always when 0.3 grams are reached in the trap, and we want to stay below 0.3 grams in the lithium as well, we could imagine such a situation in which we have a trap, let's say 2 traps connected in parallel, and we are, while one is working, the other one is exchanged with a new pebble bed. And for example, we have here a mass of 4 kilograms and temperature of 280 degrees. And we would see that the mass of the tritium in the liquid lithium and in the yttrium increases and are at more or less 52 days. After 52 days, the 0.3 grams in the yttrium are reached, and then the trap is exchanged. So we have new empty pebbles exposed to, let's say, a quite high concentration at the interface of the pebble, which leads to an incredibly high concentration gradient and an incredibly high flux into the pebble. So this leads to the fact that the new trap is very quickly filled with tritium again. And after more or less 30 days, or 25-30 days, the trap is again full and needs to be exchanged, and which would lead to this mass of tritium in the lithium and the yttrium. So the trap should be exchanged every 25 days to keep the tritium inventory below the limits. For example, if we take 20 kilograms traps, we would have like the tritium in the yttrium would increase in a very similar manner, but the mass of tritium in the liquid lithium would stay way lower. So the time interval when the trap should be exchanged seems to be independent of the yttrium mass, actually. If we take 1 kilogram, you see that the time interval is again around 25 days in which the trap should be exchanged. But we see also that the mass of tritium in the lithium would be around 1 gram, which would be above the limits. So 4 kilograms would be way better. For example, if we increase the temperature, you see how we already needed 6 kilograms to get the same result as for 280 degrees at 4 kilograms. If we have 320 degrees, we needed already an 8 kilograms trap to get the same results. At 340 degrees, we needed already a 12 kilograms trap. So you see how much importance plays the temperature. And if we take the 4 kilograms, fix and increase the temperature, you see how the mass in the liquid lithium increases. Now I planned an experiment to test my numerical model, which you see here on the left, which is simply a miniature liquid lithium loop, which consists of an electromagnetic pump, a small hydrogen trap with a bypass, a flow meter, and the idea and some lithium containers. In the bottom you see a liquid lithium container where the liquid lithium is charged with deuterium gas by bubbling the deuterium into the liquid lithium, which is molten. It is also going to be molten in this container. And then by pressing argon on top of the surface of this liquid lithium, the liquid lithium is pressed through the tube, which goes down to the bottom of the container, and this liquid lithium is pushed up into the liquid lithium loop, where it's going to circle around and go through, where it is going to go through the hydrogen trap. And then after certain time steps, you can always extract small lithium samples, which are going to be brought to a measuring facility, whereby, for example, the glow discharge method, the tritium concentration in the lithium is going to be determined. And for example, with my EcosimPro numerical model, for 10 milliliters per second flow rate, 1 millimeter pebbles, 150 milliliters of lithium, and an yttrium mass of 5 grams. I expect the deuterium concentration, for example, if we take an initial concentration of 10 Y-ppm, to fall down within 1 hour like this. And this experiment is planned to be constructed in the next 1.5 years. So in the meantime, we bought yttrium pieces to already do more investigation with yttrium metal and to get, since there are already, let's say, the solubility and the diffusivity in the yttrium is already measured, but with very big errors. So the goal is to measure these coefficients again. And therefore, for example, as a first experiment in January, we cut out of this sample, which you see here, which is very oxidized and very ugly. We cut out the sample, the uncharged samples, which you see on the lower left part. We charged them by putting them at 1 bar of deuterium and at 200 degrees for 46 hours. And then, as you can see, they changed the color, and this color indicates that it must be a hydride or a deuteride of yttrium. And then we did the so-called thermal desorption method, in which you then simply heat up the charged samples, and due to the decrease of the solubility, the deuterium is released from the sample, and then with a quadruple mass spectrometer, you can count the amount of deuterium molecules which are released. Which tells you a lot about the way the deuterium is trapped in the yttrium, and how it. And the plan now is to continue with these investigations to measure the solubility and do the same measurements with lithium, and do permeation measurements to extract more coefficients which are needed to increase to improve the numerical model and do even more simulations. So now I come to the conclusions. I know it has been a very long time as I'm speaking. So an yttrium pebble bed will serve as a hydrogen getter trap in order to purify the donor's liquid lithium loop from generated tritium. A numerical model is developed from scratch to simulate the retention of tritium from the liquid lithium into the yttrium pebbles. The model is used to simulate the tritium retention in a simplified version of the donor's liquid lithium loop, where tritium is generated with a constant rate. It is found that increasing the mass of yttrium pebbles will only slow down the increase of tritium inventory in the loop, but never leads to stationary tritium concentration. And exchanging the trap every 25 days will allow to keep the mass inventory of tritium below 0.3 grams in the trap as well as in the loop. A miniature liquid lithium loop with an yttrium getter trap is planned to be constructed in the future. Measuring the concentration in the lithium will allow to compare experimental results with numerical results of the model. Thank you very much for your attention.
So, thank you very much, Sebastian.
Sebi.
Very comprehensive and interesting presentation.
How long did I speak, actually?
Sorry?
40 minutes or something. Okay.
Yeah, too much, Sebi, too much.
I wasn't counting. So you're all welcome to ask questions by raising your hand in the participants box that you'll find in the bottom center of your menu.
Yeah, I got one.
I guess, Sebastian, you can handle the question if you can see the hand.
Okay, yeah, I saw your hand.
All right. So a couple of things. First, Sebi, congratulations. I think you have done an impressive work for the Donis lithium loop, the modeling and the parametric study that you have done for the temperatures and the pebble bed diameters and everything. I think it's quite impressive. I know how EcosimPro works, and I think you have done quite a nice job.
Thank you.
Then first of all, curiosity, do you already know where Donis or IFMIF will be constructed, or not yet? Not info from that side.
It is not finally decided yet, but if it's going to be in Europe, it's going to be in Granada.
Oh, okay.
And so I talked with several people, and they were all quite, let's say, sure that it's going to be in Granada rather than in Japan. So because in Granada, the site is already chosen, it's simply way better organized already.
Yeah.
I thought that was true for Donis, but not necessarily true for IFMIF. Like, I thought IFMIF might be distributed. Like, there's several components. Maybe the Japanese will get something. Maybe, yes. But the thing is, IFMIF is probably going to be... Okay, in the end, it's just adding another accelerator. Maybe they need to also improve. They would, for sure, they will improve things also. But I think it's going to be then to start with the construction in 2035 or 40. I don't know. So
yeah, the main thing would be to just add an extra accelerator, and that it's easily done if you already have one there.
Exactly.
I would say.
I see it like that. Yeah.
But okay, so 2 follow-up questions. If you go to slide number 6 at the beginning, okay, one more there. Okay, there. The boundary condition, the equilibrium chemical potential. Correct me if I'm wrong, because I don't quite understand the use of the Seebeck constant, the ratio between the Seebeck constants of yttrium and lithium as a way to obtain the different concentration in between the lithium the concentration in lithium and in yttrium. Because I think that the Seebeck constant works more for how you call it, for dissociation and recombination surface reactions. But since the hydrogen isotopes are going from metal to metal, even if it's liquid metal, it could be they would already be in the form of atoms in liquid lithium. Shouldn't make more sense to use Henry's law and Henry's constant to achieve this proportionality, because Henry's law deals with monoatomic particles.
I mean, in the end, I think Henry's law, it would be Henry's law, yes. But I think Henry's law is simply saying that the concentration is proportional directly to the
pressure,
pressure. And the coefficient would be also, let's say,
it has Yeah. Okay. Okay. So it's a matter of the coefficient, not of the physical reactions, physical
Yes.
happening.
So
Okay.
so in the end, what you have, okay, you have the equilibrium of the chemical potential, and the chemical potential can be expressed connected with the concentration, or connected with the pressure in a gas and the concentration in the material. And the thermodynamic expression of this chemical potential you find in the Sievert constant, let's say.
Okay. Yeah.
And it's called Sievert constant rather than Henry's constant, I think.
Yeah. No, because the picture that I have in mind in order to use this Sievert constant is like if you would assume like an internal gas pressure inside the metal, and that's what I thought, that it could be it could make more sense to use the Henry's law constant instead of the Sievert constant. But if you are telling me that it's a matter of the coefficient and not of the actual physical reaction, then I would actually agree with you on that.
Yeah, here I can show you that it's easier to I just show you that. Oh, see it.
Okay, Sebi, it's confidential there, you asshole.
No. Just that you see it here.
Words.
So viscosity in the 2 meters. Yeah. That's what I. Okay, yeah. Okay, all right. I see it now. Yeah, I think I remember seeing this this report, or part of this report, when I was at CIEMAT. Yeah, I think I recall now. Okay. Yes.
Yeah, I mean, I also need to. But the thing is, in the end, it's simply it's simply the chemical potential.
Yeah. All right.
Which you have, and it's the multiplication with the concentration.
Yeah. All right.
And yes.
Okay. And then a follow-up question. This is regarding the experimental part. So you're gonna push the lithium into the loop from the tank of where you dope the lithium with deuterium, and then you push it with argon. Have you calculated whether there will be any argon soluted in the lithium, or the solubility of argon in lithium is just rather slow? It's rather low.
To be honest, I never thought about that, but I think it's must be very low. I mean.
Yeah, I mean, I think
it's already
a noble gas should be very low, but I didn't know if you actually checked it and did the numbers, or you just assume negligible solubility of argon in lithium, in liquid lithium.
Yes.
That was the question. Okay.
I assume that.
All right.
Actually.
Yeah. I mean, makes sense. I was just curious about that.
Even if there was argon inside, it would be quite. I mean, it would just occupy more, let's say, sites where then the tritium could not
dissolve. Yeah, and exchange. Yes, exactly.
But if you have a very quite low concentration, I think, and as usually, for example, if you for example put a lot of tritium into yttrium at a very high pressure, it means that the tritium creates bonds with the yttrium, and it forms a very dense structure where no more tritium
like hydrates.
Yeah, and hydrides. Yeah, but with argon this can't happen. So if this can't happen, I think it would not really bother the entrance of tritium.
All right, cool. I'm good. Thank you, Sebi.
No problem. Thank you.
So I actually can't raise my hand, but if you don't mind, I'll go next.
Why can't you raise your hand?
I think because I'm the host. I was like trying, but
you can raise. You can do.
But I can raise it like. Well, it's great that Alex asked so many questions and actually answered a lot of mine. So that will save us some time. But especially what happens to the, I was curious about what happened to the tritium with the yttrium, if it was just sort of dissolved in the yttrium, or if it was or if it actually reacted with the yttrium, and then if you had some ways to extract it and, you know, maybe even sell that tritium, because I understand it's a pretty expensive
yeah, I mean, what you could do, for example, is
right now you
outgas it.
Money back for the research.
You can outgas it and kind of from the yttrium pebbles and try to store it somehow. But actually, it's best stored in yttrium getter, because it's best stored in a getter. And what you could do is, there are several methods would be possible to even store it better.
Yeah, and then yttrium is kind of expensive too, right? So you would want to get your yttrium back to.
I think this depends. This would be quite, I think.
Especially
it would be nice.
Change it every 25 days.
This would, for example, require research if this is possible, because never really there. I mean, there's just one article in which they also use a miniature hydrogen trap, but from Japan you almost get no information about how they did it. But I don't know whether it would be easy to, because, for example, it depends a lot on the pressure, on the concentration. If the concentration is very high, or the pressure is very high, you force that these bounds of hydrides are formed, and they are they don't, how do you say, liberate very easily anymore.
So you would need to rise the temperature very much to avoid this hydrate formation in the yttrium, I would say.
Yeah, and for example, we did an experiment in which we raised the temperature up to 1,000 degrees, and although the melting point of yttrium is at 1,500 degrees, the yttrium mold has molten, and then the oven was broken. So
maybe it was because it changed its crystal lattice due to the doping of hydrogen or deuterium, and then it changed the melting temperature.
That's also what we thought. I thought that. But the thing is, we can't really investigate that so well, because I mean, there you see already, you can investigate in all directions. Somebody that takes me focus on one thing, so that I get.
It's quite an open field. Yes.
Yeah, because almost everything is unknown almost. And if, for example, the solubility or the diffusivity are measured in the 70s or 80s, and you can't. And since then, everybody's using these values, and if these values are not so well measured, it might be that all the design is wrong. For example, you see it with Eurofair diffusivity measurements. Or solubility measure, or permeability of tritium or deuterium in Eurofair. The measurements vary by 4 orders of magnitude or something.
Yeah, I know. I've seen them, Sevi. I've seen them. Okay. All right. Yeah, Alexis.
Yeah, maybe a slightly more general question. Could you tell us a little more about the objectives and facilities that should be available at IFMIF in the future, and maybe on the specifics, like why 2 beams? I mean, I know we'll start with 1, but why do we eventually need 2 beams? It sounds.
I think just to increase the kinetic energy of the deuterium.
All right. To increase the kinetic energy of the deuterium, but they're shooting. They seem to be shooting at different spots.
No. They in the end they're uniting.
Okay.
I mean, they're meeting at the same spot, and so you simply have, I don't know whether you I mean, this has something to do with nuclear reactions than in the liquid lithium, for example, whether maybe you just simply have more reactions and the double amount of reactions. And also, wait, the kinetic energy is increased, no? So it's not just the amount of deuteriums.
And when you say deuteron, it's a neutral beam, right? So it has to be, it's first ionized, accelerated, and then neutralized in a stripping chamber.
Yes.
Like sort of like an NBI. Well,
yes, exactly.
Yeah.
Exactly.
Cool.
But I am also not so familiar with the part of the beam.
Okay. I was actually gonna ask this next. Like how do they make it to higher energies? Like what's the step between what we have now and what we'll have in a few years?
I mean, it's simply when it's constructed, it's gonna have that energy. I think that it was already started. The design started already in the end of the 80s, equally with ITER. And there were scientists that said that it makes no sense to build ITER if IFMIF is not there, because if we see that if we don't see that the materials are able to withstand and anyhow this neutron radiation, you will never be able to build a fusion reactor that's nicely working anyways.
Gotcha.
Yeah.
So I see that by now most of the people have left. Alex, do you have any more questions, or Ekaterina?
I'm good. Very interesting talk, Sebi. And yeah,
Thank you.
on my part, everything is good.
Thank you very much.
Thank you for your talk tonight. And
thank you.
Next talk will be by Martin Matushu, who's now doing his PhD in Japan. So on stellar radar equilibria, I believe, at LHD. So if you're interested in that topic, well, please join us next week. And again, thank you and good night.
Good night.